The world seems almost infinitely complicated, made up of thousands, if not millions, of different materials.
Throughout history, people have tried to collect, categorise and analyse them, to find some underlying pattern that would help simplify this seemingly incredibly complicated world. Now, at the dawn of the 21st century, we've made some progress to achieving that long yearned for simplification.
With the use of particle accelerators, we are starting to understand the nature of the world around us. These machines have revealed a whole array of particles which, we believe, may be the fundamental building blocks of matter. But back in the 19th century, scientists thought that everything on Earth was made of just over 80 elements. These elements were famously arranged in a periodic table by Dmitri Mendeleev. At the time, it was thought that elements were made of indivisible spheres called atoms. But each of the elements behaved in a different way. Did that mean that there were 80 different kinds of atom? And if so, what made them different? Were they different shapes or sizes? Or maybe the atoms were divisible. Maybe they were built of even smaller objects.
It was here in Cambridge that the first clear evidence for smaller objects inside the atom was found. Many of the great scientists of history have walked these streets, and one of the greatest was J.J. Thomson, who became the director of this, the old Cavendish laboratory. In 1896, Thomson had just got his hands on this new piece of kit. Now, it's essentially a particle accelerator. When this plate's heated, particles are emitted. They're accelerated by these electrodes. They pass through these two plates, across which you can apply a voltage, and they hit the end of the bulb here on a screen which glows, so you can see the beam. Now, this is a modern version of Thomson's apparatus. Again, we've got the particle accelerator, and there's a screen in there so you can see the beam glow. What Thomson did was he varied the voltage across the plates, and he measured the amount of bending as the voltage changed. That allows you to deduce the mass of the particles in the beams. Now, the lightest known particle in Thomson's day was the hydrogen atom. But Thomson found from these measurements that the particles in this beam are almost 2,000 times lighter than hydrogen atoms. Thomson had discovered the first subatomic particle, the electron.
The electron owes its practical utility to its smallness. It might parody Shakespeare, say my use is great because I am so small.
The electron was the first discovery of a fundamental particle, and it is interesting to realise that more than 100 years later, the electron is still, to the best measurements we can do today, a fundamental letter of nature's alphabet.
We can use electrons as ways to probe materials and look at the structure in electron microscopes or in big machines like this accelerator behind me. Pretty much all of everything we do in the 21st century depends on understanding the properties of electrons.
Thomson had discovered that the atom is not the fundamental building block of matter. There are smaller objects inside. So atoms could no longer be thought of as hard, indivisible spheres. But how did the electrons fit inside the atom? Thomson suggested that the atom was something like this muffin, with the negatively charged electrons embedded in a positive body. It would be a student of Thomson's that proved him wrong. The mystery of how the electrons fitted inside the atom was eventually solved here in Manchester, in this building in 1911, by Ernest Rutherford. Rutherford was, in my opinion, one of the first proper particle physicists because he used beams of particles as projectiles to explore the structure of matter. Now, of course, in Rutherford's day, there was no such thing as a particle accelerator. So he used the decay of radioactive elements to produce his beams of particles. This is Rutherford's original desk. And in fact, if you hunt around a little bit, you can detect traces of radioactivity 100 years later. Rutherford asked two of his students, Hans Geiger and Ernest Marsden, to fire some alpha particles at a piece of thin gold foil and see what happened. So imagine these tennis balls are the alpha particles. Now if the atom were, as Thomson had suggested, a kind of amorphous blob, then you'd expect the alpha particles to pass right through. And that's indeed what happened to most of them. But to their surprise, they found that around 1 in 8,000 bounce right back. After 2 years of puzzling over the meaning of these results, Rutherford realised that in order for the alpha particles to bounce back, they must hit something small and dense. So his new model of the atom was a bit like the solar system, with all the mass concentrated at the centre and the electrons orbiting like planets around the sun.
Today, we know that this picture isn't quite correct. Quantum mechanics tells us that we can't know precisely where the electrons are, but we can predict that they reside in distinct shells around the nucleus.
Rutherford's alpha particle scattering experiment was remarkably direct and simple, and it showed the nature of what the atomic structure is. By the way the alpha particles bounced off the atom, he worked out where the positive charge of the atom lives.
Rutherford had come to the astonishing conclusion that most of the atom, and therefore most of what we think of as ordinary matter, is in fact empty space. So if this apple were the atomic nucleus, the electrons would be a kilometre away.
After discovering the nucleus, Rutherford continued doing experiments, firing particles at different targets to delve into the structure of the nucleus itself. By 1932, Rutherford and his colleague James Chadwick had found that the nucleus is made of two kinds of particles, positively charged protons and electrically neutral neutrons.
The discovery in these experiments of neutrons, uncharged atoms of mass 1, has proved of great significance and importance, and has given us a much clearer understanding of the actual structure of nuclei.
Less than a century after Mendeleev published his periodic table, scientists had arrived at a seemingly beautiful simplification. All this is made of just three fundamental particles: the proton, the neutron, and the electron. Now, this was a giant step forward in our understanding of matter, but there were still phenomena that couldn't be explained in terms of just these three particles.
In the early 20th century, scientists recorded mysterious new particles bombarding the Earth from outer space. They had discovered cosmic rays, and they rushed to study them. By the late 1930s, they came to the conclusion that the experimental results could not be explained using the then known fundamental particles, protons, neutrons, and electrons. Some other, more mysterious particles were responsible.
Using cosmic rays to detect new particles isn't particularly efficient, however, because you never know when or where they're going to turn up. It'd make much more sense to make your own. Thus entered into physics this, the particle accelerator, a way of making cosmic rays in the laboratory.
Particle accelerators built in the 1940s and 50s led to the discovery of many new particles, given exotic names like pions, sigmas, lambdas and deltas.
By the mid-1960s, over 80 apparently fundamental particles have been discovered. So many, in fact, that particle physicists began to refer to them as a zoo. This was no better than Mendeleev's periodic table. Eventually, order and elegance were restored by American physicist Murray Gell-Mann.
There was a comparatively simple underlying structure to all this. And the classification, say, of the strongly interacting particles depended a great deal on symmetries and in particular broken symmetries, approximate symmetries that were violated.
Gell-Mann had noticed patterns which physicists can explain in terms of symmetries, and by identifying the underlying symmetries, he found he could explain the properties of the particles. According to him, protons, neutrons, and the whole zoo of apparently fundamental particles were made up of just 3 types of basic building blocks, which he named quarks.
Just the simple inspection of the particle chart would suggest immediately the quark scheme. So the difficult thing was not noticing the quark scheme. That was essentially trivial. What was difficult was believing that it had any relevance.
It wasn't until 1968 that the biggest scientific instrument of its time would help turn theory into fact.
Well, it turned out that friends of mine at the Stanford Linear Accelerator Center were doing an experiment, not intending it, as far as I know, to be a test of the quark idea. They used the electron beam to take an electron micrograph of the proton. And crudely speaking, they found that it was made of 3 objects with the correct charges. So it was taken as a confirmation that the quark idea was correct.
The particle accelerators of the last half-century have uncovered a family of subatomic particles with no discernible internal structure, or at least none that we can see today. The fundamental particles can be arranged into a table, a bit like Mendeleev's. But whereas there are around 100 chemical elements, there are only 12 fundamental particles arranged into 3 families. And in fact, you only need 4, the up and the down quark that make up protons and neutrons, the electron and the electron neutrino, to describe everything in the world around us. The other 2 families are identical in every way to the first, except that they're heavier. And why they're there, nobody knows. But we hope that there may be an even simpler picture. And to find out, we're going to recreate the conditions that were present at the start of the universe, less than 1 billionth of a second after the Big Bang. How do we recreate those extreme conditions here on Earth? Well, you need one of these, the Large Hadron Collider. 27 kilometres in circumference and filled with over 2,000 superconducting magnets, each at 1.9 Kelvin. That means that they're colder than the space between the stars. Inside here, we accelerate protons to 99.999999% the speed of light before bringing them into collision inside 4 giant detectors. And those detectors take pictures of the collisions 600 million times a second. These are the lengths we have to go to discover the fundamental building blocks of the universe.
And who knows, the next stage in our journey may reveal that our current picture is wrong. The universe may be simpler or very much stranger than we ever imagined. In the next programme, we look at the forces of nature, the agents of change in the universe.